Hi, I'm Prof L and welcome to Chemistry Matters. And today we are going to be talking a little more about what happens when you've got more than one stereocenter in your molecule. How many stereoisomers can you get out of that? You may think you know the answer from what I told you last time, but let's see how we go today. Last time we made a set of models and we were looking at how they were related. These are models that had two stereocenters in them, and we were looking at their relationships between each other and showing that some were enantiomers and that some were diastereoisomers, okay? So these are what those molecules look like. So we've got a CH2OH. Bear with me, folks, while I draw these out, because they will take a while, okay? And we've got an H and an H there. We then have the mirror image of this one here. So this is going to give you an OH over that side, or an HO, I guess. Let's try that again. Sorry about that. It's getting late in the day here. HO, and then on that side, again, an HO, CH2OH, and then we've got an H up there and an H up there. And then we had CHO, C, CH2OH, and we're drawing them out this way for a particular reason. You might ask, right, why draw them out like this? All will become obvious very soon, hopefully. So we've got the CHO there, we've got the C, and coming out, we've got the wedges. Remember, those wedges mean that it's coming out to you. The hashed wedges means that they are going away from you. We'll put the OH and the H and an HO and an H there, and then we'll go HO, H, and OH. There we go. Whew. So this was 2,3,4-trihydroxybutanol, if you recall from last time. And this was molecule 1, 2, 3, and 4. And you can see, hopefully, that these two are mirror images of each other, and that these two are mirror images of each other. So we said that we've got two sets of enantiomers here, and then 1 and 3 and 1 and 4 and 2 and 3 and 2 and 4 were related as diastereoisomers. Now, if you want some practice, you can now go and assign the stereocenters in each of these molecules, okay? So this is a stereocenter because it's got 4 different groups around it. This is a stereocenter because it has 4 different groups around it, etc., etc. Each of these molecules contain 2 stereocenters. And to see how good your R's and S's are, this is the 2R, 3R isomer, or enantiomer. And so the mirror image of that is going to be the 2S, 3S enantiomer, because when you take the mirror image of something, you invert the nature of the enantiomer. One enantiomer is R, the other one is S, okay? And so this one here is the 2R, 3S enantiomer, and the mirror image of that is going to be the 2S, 3R, okay? And so, as I said, these guys and these guys related as enantiomers, this and this and this related as diastereoisomers, this and this and this related as diastereoisomers. Okay. So, now, what then happens if we change these molecules just a little bit, okay? Just a little bit. So let's see what happens. So we're going to retain these 2 stereocenters in the molecule, but we are going to just alter things a touch, okay? So what we're going to do is we are going to make those top and bottom groups methyl groups. So CH3, 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 etc., etc., CH3, 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 and a CH3. Right. So how does that change things? Because we still have got our 4 molecules. Each of these molecules contains 2 stereocentres. Okay? So if we've got 2 stereocentres, then we should have a total of 4 stereoisomers. And it kind of looks like we have got 4 stereoisomers here, doesn't it? Okay? Because that is the mirror image of that, and that is the mirror image of that. So let's now just check and make sure that that is actually the case. Okay? So we are going to, now this is going to be a little bit difficult because they're not going to sit by themselves, but let's see if we can get these in the right orientation to show this particular point. Right, hopefully you can see that from above. And so this is this one here, and this is this one here. Right, you can see that they are mirror images of each other, can't you? Okay, so the green ones are the OHs, the whites are the H's, the blacks are the carbons, okay? And remember, these wedges mean that they are coming out towards you. These hashed wedges means that they are going away from you. So this is the exact view of these guys that we have, okay? Right, you put a mirror down the middle of them and they are mirror images of each other. Absolutely they are. Right, so we have shown that to be a fact. And you can see it even more clearly like that when they sit down like that, okay? Mirror images. Can we superimpose them? Again, we can twist them any old way we want. No possible way. So these are absolute enantiomers, okay? These are definite enantiomers. So this and this are related to each other as enantiomers. So there's 2 stereoisomers right there. Good. What about these guys now? Okay, so we are going to look at these now. Right, so these are the views of these particular compounds here, okay, or these molecules. So let's have a look at them. Again, you can see straight away that they are absolutely mirror images of each other, aren't they? Okay, they are definitely mirror images of each other in those particular views there, in that particular view there. When they sit down, you can see definite mirror images. Right, absolutely. Do they contain stereocentres? Yes, they do. This carbon here has 1, 2, 3, 4 different groups around it. This carbon here has 1, 2, 3, 4 different groups around it. So there's 2 stereocentres in this molecule. There are 2 stereocentres in that molecule. But what happens if we try and superimpose them? Uh-oh. Look at that. Holy moly. You can superimpose these molecules. Which means that these guys are not isomers of each other. These guys are the same molecule. Okay? How can that be, though, you say? How can that be? Because look, they are mirror images of each other. They contain chiral centres. Both of those carbons are chiral. They're stereocentres. They have 4 different things around them. So they should be non-superimposable mirror images of each other, but they're not. They're the same molecule. And the reason for that is that this particular orientation of the molecule, unlike these guys, contains a plane of symmetry. And this is what stereochemistry is all about. It's all about symmetry or the lack of symmetry. Now, look at this particular molecule here. It might even be clearer viewed from above like that. If you chop that in half, or if you put a mirror straight down that bond, that's going to go onto that, that's going to go onto that, and that's going to go onto that. This particular conformation of the molecule, or configuration, should I say, of the molecule, has got a plane of symmetry. As has this one here, which is not surprising, seeing it's the same molecule. You put a mirror down there, and you will see that that maps to that, that maps to that, that maps to that. So this configuration of the molecule gives you the same molecule. The mirror images are superimposable, even though you've got stereocenters in there, and that is a special type now of isomer, if you want to call it that, which they're not really isomers. We call them, in fact, meso compounds. Okay? So meso compounds are compounds that contain stereocenters, but which also contain planes of symmetry. And that then makes them the same. They are the same molecule. Now that doesn't work, as we've already shown, for these guys here. Now these guys, yes, they are mirror images of each other, and they contain two stereocenters, but you put a mirror down here, that maps to that. That maps to that, no way, okay? You don't have a plane of symmetry down there. And same with this one here. You don't have a plane of symmetry that cuts that bond in half. That will map to that, that will map to that, doesn't work, okay? So these guys are true stereoisomers. They are enantiomers of each other, okay? They are related as non-superimposable mirror images. Put your mirror down there. Yes, they're mirror images of each other, but no, they are non-superimposable. These guys, yes, they are mirror images of each other, but now they are superimposable because of the presence of that plane of symmetry down the middle there. Now you may recall in the last video I said, right, the maximum number of stereoisomers that you can get is 2 to the power of n, where n is the number of stereocenters that you have in your molecule. In this case, these molecules contain 2 stereocenters, okay? So therefore, we should have 4 stereoisomers. In fact, we only get 3. We should have a maximum of 4 stereoisomers, but we only have, in practice, 3 stereoisomers because this molecule is symmetric, okay? And it's symmetric because when we looked at the last molecule, we had a CHO group up the top and we had CH2OH group down the bottom. And that took away that plane of symmetry that now exists in these configurations, okay? So, very, very interesting that, and a very, very important concept to get your head around. It really is. If you're going to go on and do organic chemistry, you're going to be dealing very probably with molecules that have numerous chiral centers or stereocenters. You've then got to be able to figure out how many possible stereoisomers you're going to get for a given number of stereocenters, taking the symmetry of the molecule into account, okay? Very, very, very important stuff. Okay, we're going to finish on a topic that I've just used words for that I haven't yet explained, and so let's do that. And I've been using the words configuration, excuse me, and conformation, okay? So let's have a look at the meanings of those 2 words in terms of these little models that we've got. Now, here we're back to our original non-superimposable mirror images of each other. These are, remember, enantiomers. So one of this is R and one of this is S, okay? Can we convert one enantiomer to the other one? And the answer is sure we can, but in order to do that, we're going to have to break at least one bond, okay? So let's show that physically. Let's say we want to turn these molecules into the same molecule. So what I'm going to do is I'm going to take this green and this blue and I'm going to swap their positions. So let's swap the green and the blue. So the blue now goes there, the green now goes there. And, okay, so you will see that they are now no longer mirror images of each other, are they? And really importantly, now you can put them on top of one another. So now they are superimposable. So they are no longer mirror images, they are the same molecule. Now, anytime we do that, anytime we convert one enantiomer to another, we are changing the configuration of the molecule, okay? So configurations of molecules, and whoops, I've done this around the wrong way. Configurations of molecules, changing configurations involves breaking chemical bonds. You have to break bonds and remake bonds in order to change configurations, okay? And again, I've done it completely wrong. I don't know how I managed to do that. As I said, it's late in the day, so there we go. We're back to our original configurations now. So we talk about an R configuration, an S configuration. To change the configuration of a molecule, you have to break and make bonds, okay? To change the conformation of a molecule, all you have to do is rotate around bonds. So this particular molecule here has got different conformations depending on whether the atoms line up or not, okay? And we've got a whole lot of different possible conformations of this molecule. You can have the carbon atoms lining up, you can have them halfway in between, you could have the carbon and the hydrogens lining up, and these OHs lining up, etc., etc., etc. And in fact, there's an infinite number of possible conformations of this molecule depending on how far we rotate around that single bond, okay? So that's the difference between conformation and configuration, which are two very, very widely used terms in organic chemistry, and you will need to understand the difference between them. To change a configuration, you have to break and make bonds. To change a conformation, you simply have to rotate around bonds. And we're going to come back to that. That's going to be very important when we start looking at, if we ever get there, cyclohexanes. Right, I think that will do for the time being. So thank you for watching, thank you for listening. I hope you learned something, and we will see you in the next video. See you later.